the good thing about switching from half an hour is that people will probably know for half an hour. It's different, really. Okay, so we have to have Chris Maynard here from the Met Office. So I first met him when he was studying landscape PhD student in Edinburgh, and then he had a personal key part fellowship in Edinburgh, another postdoc in Edinburgh, ended up a software manager, and then he moved into Edinburgh Parallel EPCC in Edinburgh as well. So I was surprised him a couple of years ago to say, I'm an Exeter now. I'm like, whoa, man. So he moved over to the Met Office to tell us why he changed that. And I met him at the Dirac Supercomputer meeting earlier this summer, and he said he was interested in talking to the 5 master groups, numerical groups in the southwest, and perhaps doing some things, many placements and stuff like that. So I'd like to introduce Chris to give us a talk on.
Thank you, Craig. Thank you for inviting me, and thanks for the introduction. So, in fact, I am a QCD refugee. I spent quite a lot of time in Edinburgh writing solvers for QCD and various applications, and now I write solvers for the Met Office. So if you give this slightly cheesy title, Fast as Lightning, Supercomputers, Solvers and Software for Weather and Climate Models. So Craig introduced me, so I thought I'd just introduce the Met Office. So we're a UK government agency, and our purpose is to work at the forefront of weather and climate science for protection, prosperity and well-being. And we've been doing it for quite a while. So we were founded in 1854 by Admiral Fitzroy. I notice there's a Fitzroy building here at the University of Plymouth as well. So Fitzroy was the captain on the Beagle, Charles Darwin's voyage. So we've been around for about 160 years. We're quite a big organisation, turnover of more than 200 million, about 1,900 staff, quite a few are based at Exeter. But we also have quite a few manned locations and quite a few all around the world, and also 2 mobile Met units which go wherever the UK military go. So what do we do? Well, we do the UK Public Weather Service, which is the thing you're probably most familiar with, which is where most people get their weather forecasts, including most of the television broadcasters. We also do severe weather warnings to emergency services and the Maritime and Coast Guard Agency. We provide forecasts for all the UK military services, and in fact the US Air Force uses the Met Office Unified Model as well. We are the primary provider of weather information for global air traffic control. We provide weather and climate services and data to the global insurance industry. We can track environmental disasters, so nuclear fallout, volcanic ash, forest fires, etc. We have atmospheric pollutant models. We provide UK data to the UN IPCC, International Panel on Climate Change, and we work closely with environmental agencies, emergency planners and crisis response experts and aid agencies to develop capacity in developing countries as part of the WHO, or WMO, World Meteorology Organization, which is a UN agency. So the Met Office does quite a lot of stuff. So we also do a lot of computing. So we do supercomputing as well to run the models, which is what I'm going to talk about, but that's not the only sort of computing the Met Office has to do. In fact, have to do pretty much any kind of computing you can think of. So we have to collect all the various data we need, and we have to, as well as running the models, then we do various kind of visualization, which is scientific visualization, as well as pushing this out for public consumption or particular customers. have to look after the data, collect data. We also do space weather. So the Met Office is a whole range of things, not just what I'm going to talk about. Okay, so if you're going to do a model of the atmosphere, there's quite a few things that are quite specific to doing an atmosphere, quite specific to the domain. First one being geometry. It's spherical, well, mostly spherical. It's oblate, and then you have mountains that stick up, so it's not exactly spherical, but it's mostly spherical. So in meteorology, mountains are called orography. The other thing is that the atmosphere is very thin, and it's vertically stratified. So, depending on what you count as being the edge of the atmosphere, there's something called the Kármán line, which is about 100 kilometres up. It contains almost all the content of the atmosphere in terms of mass or density. And above that, it's not really a gas anymore. I mean, there's still particles, but it doesn't. They're so far apart, it's not really a gas. So, most models wouldn't go above 100 kilometres or something like that, because that's pretty much the end of the atmosphere. But this diagram is drawn to scale, but I've drawn it with a 600 kilometre atmosphere, because if I try and draw it with only a 100 kilometre atmosphere, you can't see it, it's too thin. So it really is very thin. It rotates quite fast. It's not in thermal equilibrium, because there's a nice star shining on one side, and it rotates. Then you have the atmosphere, you have the ocean, you have ice and sea ice and land surface, and they all interact with each other dynamically. There's moist chemical and biological processes that change the behaviour of what's going on. So it's a pretty complicated system. So it's a very complex domain. It's multi-component and it's multi-scale. And the models that we use to predict what's going to happen are large, of order a few hundred thousand and millions of lines of code. And legacy, they can take a decade or more to develop, and they will probably have a lifetime of at least quarter of a century, if not more. They undergo continuous development. For example, in the unified model, we probably have about a code churn of about 20% every year. That's like new scientific development coming in. We want to run them in operations and production, so naturally they're very conservative. Which is just scientific prudence, because there's so much going on. You don't want to change things unless you actually know what that change entails, what that change means, and hopefully you get a better forecast that comes out. Okay, so here's a nice picture. You might recognise it's over Devon. So we're down here in Plymouth somewhere, and I normally am up here in Exeter. There's some nice things to note about the picture. There's, it's a satellite picture, so you're looking down from the top. So you've got cloud tops over here, which are higher up than these things here. And if I was a meteorologist, I'd be able to tell you what those patterns are, but I'm not, so I won't. But the point is, you can see nice structures forming that are at very different scales, even just over Devon. So what goes into a model? Well, you have to solve the so-called primitive equations, which are those things there. So that's the dynamical core. It's an initial value problem, partial differential equations, and the equations for motion, equations of motions for density, humidity, pressure, temperature, and wind, mass conservation, and thermodynamics. Okay, so that's just the dynamical core. But that's not all you have to do, because stuff moves around. We have advection, which is stuff blowing around, and convection. There's physical parameterizations for things we don't actually resolve in the dynamical core. So radiation, how energy comes into and out of the system. So you have solar radiation coming in, and then that gets reflected and re-radiated by different processes. There's cloud physics. There's precipitation, and stuff just falls out the sky, rain, snow, ice, etc. And if you put all that together in the Met Office unified model that we use for numerical weather prediction and climate modelling, that's about 500,000 lines of Fortran, MPI and OpenMP. But that's not enough to model the atmosphere. We also have to do land surface processes and atmospheric chemistry. And if you want to run for anything longer than a week, you need to dynamically couple to the atmosphere to the ocean, because that's a dynamic feedback between each other, and couple the atmosphere to the sea ice. And then we also have to have observations, data assimilation and configuration management, which is written in Python. That's about 2 million lines of code. So that's our whole modelling system. So how do we start? Well, we have to start with observations. We have to measure the state of the atmosphere now, and that turns out to be quite hard, because for an initial value problem like the atmosphere, it doesn't matter what resolution you have, you always need more data. So we never have enough data. So we collect all the data we can, We process more than 100 million observations a day. Most of that is observations from space, from satellite data, but in fact we will collect data from anything we can, because we never have enough. So this is just a series of animations that show you all the different sorts of the geographical and temporal distribution of the data. And the thing to notice, it's really lumpy, right? It's not uniform at all, right? So the satellite data actually comes in stripes because they come in from polar orbiter data, which are about 1,000 kilometres up. Geostationary orbit is too far away, it's 36,000 kilometres, that's too far. So the polar orbiters, you get a stripe of data every sort of 15 an hour, or every hour or so, and that stripe moves across. So that's temporally lumpy as well. We have buoys floating in the sea to collect sea surface temperature data, and all this kind of stuff. So it's very lumpy, and there's not enough of it. So having more data to start with definitely improves the forecast. In fact, we'll collect data from any source we can. So in fact, I discovered recently that we are collecting data from seals. So it turns out the Sea Mammal Research Unit at the University of St Andrews have attached sensors to grey and harbour seals to record their behaviour and environment, to see what the effect the environment has. So they're recording the sea surface temperatures and profile as they dive down, and the salinity, and we don't have this information. And now they can provide it to us tracking in real time. So this is some seals where they've been in the North Sea, and so this now gets processed by the Met Office as well as part of the forecast that we do. And then it turns out apparently we've actually been doing a similar thing for elephant seals in the Southern Ocean for a while. Obviously Met Office hasn't gone and tracked the mammals, someone else has been doing that, but the data is available, so we've grabbed it. So data assimilation. So we have all this data which is very lumpy and incomplete. So actually our best guess for the first state of the atmosphere now is the output of the last forecast. Okay, so we actually measure the state of the atmosphere. So that's what's supposed to be represented by this blue line here, is for some observable. And then we have to compare that to some observations. And both the forecast model and the observations have errors in them. And so we have to do a process called data assimilation, where we try and adjust what we think the state of the atmosphere is now based on observations, but mostly comes from the output of the last model. So to compute the model state from which the resulting forecast best matches the available observations. As there's a four-dimensional variational analysis process we go through called data assimilation. So that gets us the state of the atmosphere now, from which we can then run forward in time to do a forecast. So, but of course we don't just do one forecast, we do lots of forecasts. So this is the our current configuration that we've been running in since September 2000. Oh, sorry, since the summer actually. So we do a 10 kilometre resolution global model, and that's the so-called deterministic forecast. And then we run an ensemble of 18 other forecasts at a lower resolution, 20 kilometres, to kind of calculate the error in that. And I'll tell you a bit more about ensemble forecasting in a minute. So that's not one forecast, that's 18. It has about 70 levels with 80 kilometre lid. We do a 48-hour forecast twice a day, and a 6-day forecast twice a day, and then run this hybrid 40-var data assimilation process once a day to start the forecast from. And then we have a high resolution forecast over the United Kingdom, which is a 1.5 kilometre resolution deterministic, and again an ensemble of 18 members at a slightly lower resolution of 2.2 kilometres, 70 levels, but only a 40 kilometre lid this time. And we run that many times at a 12-hour forecast, a 54-hour forecast, and 120-hour forecast, variously 16, 6, and 2 times a day, again with a 40-var data assimilation. So the forecast is forever running, and the forecast suite is forever running in an ever ongoing thing where we keep updating our data all the time. What comes out of the forecast. So that's what our current operational configuration is, and that uses some fraction of our supercomputing resource, but also we do research into trying out new models as well, and also climate production runs as well. Okay, so what do I mean by an ensemble? Well, okay, so we have an initial value problem, which people call chaos. And there's this great flap of the butterfly's wing can change the path of a hurricane. Actually, it came from a meteorologist called Edward Lorenz, and what he actually said was one flap of a seagull's wing can change the course of the weather forever, because if you're uncertain in your initial conditions, you can end up on a different trajectory and end up in a different forecast. So we actually, because it's very difficult to do deterministic forecasts with complete accuracy, what we do is perturb our initial conditions and then start multiple forecasts from that. And so what we end up with is this kind of idea of an ensemble of forecasts. And so when we give a probabilistic forecast, i.e. it's 30% chance of rain, that's because some of the ensemble members have predicted rain and some haven't. That's literally what's occurring. So we kind of calculate the error by doing multiple forecasts, but that's 18 times the computational cost, for example, to do 18 ensemble members. Okay, so what do we use it with? So this is, what do we do it with? This is a picture of the Met Office supercomputer, garish purple for no apparent reason, as far as I can tell. But it is quite big. It is 36 cabinets of Cray XC40. So the Met Office got, you may have heard the announcement in the news a couple of years ago, the Met Office ordered 100 million or 97 million pounds for a new HPC. So this came in several chunks. So we had phase 1A, which was 2 machines. So we had 2 machines for operational redundancy. So we had 2 machines initially that were relatively small, 610 nodes of Intel Haswell. And then we had phase B, which then extended that to 2 further machines of 2,500 Intel Broadwell nodes, and then finally we had to build a new building to put it in. We had 6,500 Intel Broadwell nodes. So this machine here, this is 36 cabinets. That's in the number 15 on the top 500 list that came out this week at Supercomputing, and that's just for the Met Office. So it's a huge machine. 15, yeah, 15, yeah. And it uses a lot of power. That's a 3 megawatt power supply. So, so Anton, I borrowed the power supply earlier for my laptop. Yeah, thank you. This is a 3 megawatt power supply, right? It's huge, right? Disappointingly, it doesn't have any knife switches. But you know, the reason we have an entire new building is not because we didn't have enough space. We didn't have enough power in the building. So we are power limited by by where we can go with supercomputing. And this is a bit of an issue because the sort of lack of Dennard scaling in process design, which means whilst you can put more processors on an area of silicon, which is Moore's law, you can't turn down the voltage and still get them to switch. And if you can't turn down the voltage, then you're just putting more energy into the silicon, and so it'll get too hot. And so you can't make your processors run faster. So since the year 2005, pretty much we haven't had any faster processors. We've had more processors, but not faster processors, because this lot here comes to about 500,000 computing cores. Right? And that's a lot of parallelism to try and exploit, when actually what I wanted was a 500,000 times faster computer. Right. So this is tricky. So this is a paper here that was presented at ISC 2015 by Peter Kogi, called Updating the Energy Model for Future Exascale Systems. So basically it says, if you keep doing CPU processors design, with all that entails and all the power consumptions, can you make a computer capable of doing an exaflop for 20 megawatts? And the answer is no, you can't. Right, so this is a picture of him saying, "Oh, twist, can you have some more power?" No, you can't. There isn't any more. I mean, there's 3 megawatts. I mean, that's that's £3 million a year to run just the electricity bill, right? So, we're really up against what we can do with current computing technology. So, whilst we can certainly exploit a supercomputer like this, we can't keep going down this road of just having more cores and using more power, right? So, at some point, we have to do something else instead. So, if you're going to do something else instead, you have to look at different sorts of processors. So this is looking at architectural complexity. So this is a processor called Intel Xeon Phi, or Knight's Landing. So this is something which is supposed to be give you more computing for more parallelism for less power to get to performance, because you can't have more performance by being faster. So things to note about this processor: clock speed is low. It's only about 1 gigahertz, whereas Broadwell's about 2 and a bit. The previous Met Office supercomputers were IBM Power 6 and 7, and Power 6 had 4.3 gigahertz. Now we're down to 1 point something. So they're not getting faster, they're getting slower. There's 36 tiles, pairs of cores. There's a pair of cores there. So there's 36 tiles, 2 cores per tile. They each can run 4 hyperthreads. They've got a shared level 2 1 megabit cache, that's in red. They've got 2 512-bit wide single units on board, so that's a lot of parallelism there. So you've got to do instruction level parallelism as well. There's these so-called fast memory, 8 memory controllers to MC DRAM, which is fast at 400 gigabytes per second. That's really nice. There's not very much of it. There's only 16 gigabytes. And you've got traditional memory DDR, which is sort of slow memory, much slower, say 90 gigabytes per second. You have as much as that as you like, effectively, but it's much slower. So I've got memory hierarchy as well. I've got 2 different memory spaces to put things in, and they operate at different speeds. So that's fun. Now, those of you who are good at counting will notice, in fact, there are more than 36 tiles on there. There is, in fact, at least, depending on what clock skew you buy, at least 2 of them are never switched on. So it's a very complicated processor, and at least two of the tiles are dead. So that's a processor that's supposed to deliver the same performance as Broadwell, but you can use less total power, but it's much more parallel, so it's much more difficult to use. So you've got architectural complexity you've got to exploit. How are you going to do that in software? So where are we with how much supercomputer can we exploit at the moment? So this is the scaling of the unified model on Cray XC40 Broadwell, and I'm comparing 2 different things here. I'm comparing the global model and a limited area model. Okay, so the global model is across the whole globe, limited area model is just a small section but at a higher resolution. Okay, so I've normalized these to the second data point here, which is then 1, and they both have a similar number of data points per amount of parallelism, so say per MPI task, about 2,500 at that point there. So the blue is the local area model, and the red is the global. Okay, so as I increase the amount of computing resource up to like 10 times as much computing resource for how much faster does it go? And as you can see, that's perfect scaling, and it scales off. This is running at some fairly pretty extreme scaling. So it's a strong scaling, so the number of data points goes down as they go to the right, and then I'm running at pretty much the whole of the phase 1B machine, so up to 88,000 cores, and so this is going beyond our current 10-kilometre model. This will be looking at a 6-kilometre model. What could we do next? And we'll start to struggle to see scaling out that far to go beyond where we are now. And the reason is that we can see the LAM is much more efficient than the global. It's got better load balance. So, for example, there's no problem with load balancer. So shortwave radiation, that's sunlight. So half the globe's in sunlight, half's dark. Okay, so there's a load balance problem there. If you're a local area model, you don't have that problem. There's no parameterized convection. It's mostly over land. And we don't have any problems with advection around the poles, which I'll come to in a minute. There's also no I/O in this analysis, and this particular analysis was the data file for that was 192 gigabytes, which is like pretty big, but it's not so big you can't, it's not inconceivably huge. But to load that into a machine to 88,000 cores, that takes almost half an hour. And the global model's got to run, the whole thing's got to run in an hour to fit in this global cycle. So it's like, I can't spend half an hour reading the data before I start. So, we have some hopefully known improvements will help, but we need more software, algorithm and technology to get going with that. So that assumes that we can read in the file much faster than we actually can. So what's going on here? Well, okay, so the Met Office unified model runs on the longitude-latitude grid. So there's good reasons for this. It has nice mathematical properties, but for example, at 25 kilometre resolution, the grid spacing near the poles is 75 metres. At 10 kilometre, we're reducing down to 10 metres. So it's we have a pole problem because basically it's singular at the poles. So we have the grid is not, the globe is not, the grid we have is not uniform at all. So in fact, if you look at the shape of these things, they get extremely long and thin near the poles. The ratio just gets just gets very ridiculous. And we like the long latitude grid because it has a mathematical discretization called C grid, which means you have orthogonal degrees of freedom. That gives you nice symmetry properties, which is why people like doing it, but it's going to have a problem with scaling. So the Met Office decided in 2010 that they would start again. So they would start again, completely have a brand new model completely. So they came up with this project called GOKHO, which was jointly with academics at Exeter and Imperial and Leeds and quite a few other places to look at a completely new mathematical scheme for discretizing on a quasi-uniform mesh. So it wouldn't have a whole problem. So to have a scalable dynamical core. And the idea of doing this as an unstructured mesh rather than a structured mesh. So that project's formally ended, the collaboration continues, and we're looking at developing something on a cube sphere, which is an unstructured mesh, but doing it as an unstructured mesh with a mixed finite element rather than finite difference dynamic scheme. So the model we're developing is called Elfric, after Lewis Fry Richardson. So Lewis Fry Richardson was originally a Met Office employee. In 1916 he resigned from the Met Office to join the Society of Friends ambulance service on the Western Front because he was a Quaker, a Society of Friends, so he's a conscientious objector, and he did the first ever numerical weather prediction calculation to try and solve the equations 100 years ago. And he was doing it whilst he was 100 years like this month, so he was actually being an ambulance driver at the Battle of Passchendaele, whilst he took 6 weeks to do the calculations by hand for one grid point. So anyway, so we're building a new dynamical core, and we've called it after Lewis Fry Richardson because he was the first person to try and do this. So here's a picture of a cube sphere. So basically, you have a cube, and you kind of blow into the corner, and you sort of distort it into a sphere. But the distortion of the cells is much smaller than there would be for a long lat grid. So it's quasi-uniform, and so there's no singular poles like the long lat grid. It's an unstructured mesh, so we can change to other meshes if we want to. We're developing this mixed finite element scheme, this so-called C grid, and this gives us an exterior calculus which has mimetic properties, i.e. it mimics the properties of the continuum calculus we want to have, and we're semi-implicit in time for doing the time stepping. So our fields will then live in these different spaces here. So lowest finite element order method, then you have these 4 different spaces, and you can see that things will be depending on what kind of calculus properties you want to have. They will live in different spaces, whether they're scalars or vectors. So that's a diagrammatic representation of that there. So some of the scientific aspects: it's a mixed finite element discretization of the non-hydrostatic compressible equations. Flexibility built in, so we can change in principle the type of grid and the accuracy by using go to a higher order method if we wanted to. We're targeting the cube sphere and lowest order elements, again similar to C grid. Compatibility carries over a number of desirable properties of mass, for example mass conservation from the continuous equations to their discretized form. Transport schemes being developed, so it's called Cosmic. There's a couple of things there. And the time discretization is a semi-implicit iterative scheme like it is in the current unified model. And we've started work on looking at coupling this to physical parameterizations from the unified model. So people do dynamics research when they want to show how well is this working. They show you nice swirly pictures like this. Okay, so this is a cold bubble test. So you drop a cold bubble into warm air and it hits the bottom, and then you get nice swirly patterns. So this on the right here is the current unified model running, which has lots of nice properties which they'd like to retain for GOKHO, but do it on the unstructured mesh. And then this is the version for GOKHO, and as you can, and the idea behind these two plots is they look pretty similar. They're showing the same kind of properties. This is something called baroclinic flow across a sphere. So you start off with some disturbance in the northern hemisphere, and you see how it propagates through time after 10 days. And they're not the same, but they're looking reasonably similar. So this approach seems to be promising, is what these plots are supposed to show. We have to write some software to do this, though. So we're starting completely from scratch. So we're going to have to write some software. So we need a programming model. So Fortran. You've heard of Fortran, right? Okay. Here's some Fortran. Okay. It's an abstraction of numerical mathematics. The implementation and architecture is hidden, and then we have some code, which is just text, which conforms to the semantics and syntax of the language definition, and we have a compiler, which transforms the code into machine code for specific processes. So we have a nice separation of concerns between the abstraction of the mathematics, which we want to do, from the machine hardware, which we don't really want to know about. We want a compiler to do that bit for us. Okay, so that's nice. But then we break it. We break this nice abstraction by all the parallel performance and memory features exposed, and then we hack them back together with MPI, OpenMP, OpenACC, OpenCL, etc., etc., etc. A whole range of different things. Not only there are different sorts of things. There are libraries, languages, language extensions, directives, compiler-specific directives. This is horrible, right? I mean, here's my nice design API, how I want to write my code, and here's the one I've actually got. And not only that, there's nothing that says what happens if I switch this one to 4 and then flick this switch and then press that one to 3. Right? They don't interact with each other at all. It just depends. You've got to figure it out. Right? So this is really bad. This is a really horrible programming model, which is not good. And this is why performance parallel programming is really hard, because you're sort of pulled to do two different things at once. So if we were starting again, could we try and get people to maintain this separation of concerns between scientific programming, which is to find a numerical solution and estimate the uncertainty of certain mathematical equations, and the parallel programming and optimization methods by which large problems can be solved in real time. Right, so we just want to separate the concerns. We don't want to mix the two things up. You don't keep your toilet brush in the fridge. Right, you put it in a different box. So you want to have the sort of optimization stuff over here, and then have the scientific code somewhere else. And it's about the code. You want to separate the concerns in the code. So we have a layered architecture. So we have an algorithm layer where we have a high-level expression for the operations on the fields. And we have a kernel layer, which is a low-level explicit common operation on a single column of data. Okay. Code has to follow a set of rules, which we call this Cyclone API. It's effectively a domain-specific language. But if we do that, then the parallelization system and horizontal looping can be separated out into the parallel layer. So they're separate from each other. So this is similar to, you may or may not be familiar with other constructs in finite element code called OP2 and PyOP2 and PyDrake. These were developed by Oxford and Imperial, and we talked to them quite early about how we might do this. So it's kind of replicating something that's already been done. But you separate these two things out. So in order to do this, we need to think about a little bit what we're going to do. So we have extra information. We have kernel metadata. So in your kernel, when you want to write what the kernel is going to do, you have to write down what the kernel is going to do to tell the system so it knows how to do the parallelization. So we have these data access descriptors. Now we've embedded the whole lot in Fortran. Okay, so this is all Fortran, but it's not really used as Fortran. It's actually read by something else. So the science developers can just write Fortran, and in fact we can generate then the rest of the kernel stub from this, and then we have a code generator which reads the metadata and then generates the parallel code in its entirety. So it's a Python code generator called Cyclone. It has a parser, does transformation and code generation. So in that sense, it really is like a domain-specific compiler. It controls the parallel code, MPI and OpenMP, and in principle OpenACC if you want to look at running on GPUs as well. It's developed by some our partners at STFC Hartree Centre, which is Rupert Ford and Andy Porter. And then it turns out someone else has already got the name, Cyclone. It's a Lego character, and he's a former weathercaster turned crazy bad guy with a craving for destruction. Couldn't make it up, really, could you? Brilliant. Right, so what does it do? Okay, so we have the algorithm code and the kernel code, and then so there's a bit of this Python code called the parser. So it just reads the file and parses the Fortran. Okay. And it generates something called an abstract syntax tree of those things. So then it can go away and generate the actual algorithm code that we're going to compile, and then there's something to generate the side layer. And then we can do transformations on that to say, okay, I want to do distributed memory for MPI, I want to do shared memory for OpenMP, and then generate that code. And so I end up with the parallel layer code as well. And does it work? Yes, it does. So this is strong scaling for global volume. So it's about 8 million cells in the horizontal. It's just pure. It's MPI, and then there's some MPI and OpenMP together. But the basic point is we just we switched on to distributed memory and then just ran straight away. As soon as we got everything to work, not only did it work, it works forever. As long as you write code to the API, you want to change your science code, change your science code, this still works. And we ran on all of the machine over the road, which is 221,000 MPI tasks with automatic parallelism. So the idea really works. So that scaling doesn't look terribly good. There's a couple of issues with that. The Intel 15 compiler had thread contention issues, which kind of support the OpenMP. We're using a library called the Earth System Modeling Framework for doing which is a wrapper around, well, not a wrapper, it does other things as well, but basically then wraps around MPI. At this point, it only has support for 32-bit integers, so I ran out of numbers. So the problem sizes on the far right is too small. We probably want to do much more than 8 million cells on the global model. So on the whole machine over the road, I basically ran out of numbers. So I had to do much too small a problem, so I was dominated by communication. But in principle, it all works, and at some point we get a 64-bit version of this library, and then off we go again. So I sort of talk a little bit about the solver. So we have a semi-implicit 3D solver. These are the continuous equations here. We do a quasi-Newtonian linearization around a reference state psi, and then for each time step, that's the top equation there basically. So you want a time step between, like the time step in the k+1 into the future. What is the state of the model then? We sort of linearize around the reference state because it's a nonlinear model. And for each time step, we then either solve this mixed system here or eliminate the variables to form the Helmholtz equation. So you've got the momentum equation at the top, the potential, temperature, advection, which is the second line down, and then the mass conservation, which is the density equation, and then the equation of state. And I thought I put the variable names on. What they are telling me? No, I've lost. Oh, there we go. So U is the velocity or wind field. Theta is the potential temperature. Rho is the density, and pi is the This is something called the Exner pressure functions. This is just the way the equations are formulated, but basically it is the same set of equations I showed at the beginning, written in a form that we have to solve them to do the time steps. So that's the continuous version. So you have the delta t, which is the size of the time step that we need to do. So in the discrete system with this mixed finite element scheme, then this set of four equations reduces to this linear system here. So we've got M, which is these M's are then our mass matrices. That's an operator coupling to the same finite element space. D is a divergence operator, and P is a projection operator. So I have this mixed system here. So I have to do an outer solve per time step for this mixed system, and then I do an inner solve to solve the pressure subsystem, and then substitute that back in. So the inner solve here is this set of expressions here to formulate the Helmholtz equation, where I have the Helmholtz operator on the Exner pressure field is some right-hand side, which is basically these things here with some of the fields eliminated, and I have this Helmholtz operator. I need to compute the inverse of this thing here, which has got the mass matrices and this inverse mass matrix in. So it's a fairly complicated system that I have to solve. So the outer solve is this mixed system. We do with GM-res, we're doing that twice per time step. Inner solve, just for the pressure system, which is a much smaller system, we use BiCG stab. We do that twice per time step. We need to do a pressure preconditioner for this system here. So we would like to do a horizontal matrix-free geometric multigrid, which we haven't done yet. That's in development. That's what we'd like to. We're doing that. We're developing that jointly with a chap called Eike Müller from University of Bath. And the vertical, we'd solve that exactly with a block diagonal, tri-diagonal solve. So if you recall, I told you the atmosphere is very thin and vertically stratified. So the horizontal and vertical degrees of freedom naturally can be treated differently in this system. So, and we might do some additional mass matrix inversions, or by CG stab to be exact. So these M's here, okay, I'll come to that in a second. Right, so I'll show you some scaling results. Something called the baroclinic wave test. This has the naive solver in it because we haven't done multigrid yet. Has a very relatively short time step. We want to have semi-implicit methods so we can have a long time step, so you don't have to do so many time steps. But we're still developing the solver. It's lowest order finite element on the cube sphere, 4-size Earth, only 30 levels, 30 kilometre lid, dynamics plus flux-based advection scheme. The advection doesn't have the MPI OpenMP in it yet because we're still developing the scheme. But if you look at the matrix vector routine, so the matrix vector, so here the matrix is assembled locally in the cell, so we call this local matrix assembly. So we have a finite element cell, a number of degrees of freedom per cell. We assemble that locally just for the cell, and then we have a routine that applies that matrix vector, so it's matrix free across the whole mesh. We're looking at increasing that to assembling the whole thing in the column, so it's a much bigger matrix, and then applying that operator across the whole mesh. So it'll still be matrix free horizontal, but we're fully assembled in the vertical. At the moment, we're only assembled in a cell. So at lowest order, that means that matrix is quite small. It's only, say, 6 or 12. So it's quite a small matrix. If we have quite a few levels, then that matrix gets much bigger. So this is then a profile of all the matrix vector, how long it would take for running on 6 Broadwell nodes for a relatively small problem. And this is looking at the matrix vector performance. And this is an interesting scaling plot because it's a fixed resource, so it's fully populated. So on the right, it's pure MPI, so it's 36 MPI ranks per node and 1 OpenAP thread. And as we go to the right, I increase the number of OpenAP threads and decrease the number of MPI ranks. And as you can see, OpenAP is winning, which is not always the case. Well, it is in our code by design, but that's not always what you would see just from most codes. And why is that? It's because we're doing redundant computation. My slides are out of order. Okay, so what we're doing redundant computation. So this is looking down vertically. I've got 2 cells next to each other, and I've got degrees of freedom that live on a shared entity, an edge. And if that's across a partition between 2 MPI tasks, I need to receive a contribution from both the owned and the halo cell. So both cells contribute to the value on that degrees of freedom. We're doing redundant computation into the halo, so we can do less computation. Okay, and we can choose as an optimization how far out we redundantly compute. So we could just do redundant computation in the halo cell to get this owned cell correct, or we could keep going. So at the moment, we just do one level of redundant computation, so that this one is all correct, but you still have to halo swap next time to get the information, starting information for this one. But it means we don't have to halo swap to get the answer. If that makes sense. Okay. Why is it faster with OpenMP? With MPI only, I've got 4 MPI ranks, and they all have halos. That's the green on the right. With OpenMP, the picture is on the left, and whilst it's a bigger boundary per thread, it's not. Like just from boundary to area scaling, there's literally less work to do. So if I'm doing redundant computation, OpenMP is going to beat MPI. That's what we're seeing, because there's literally just less work to do. Okay, so if I look at that, just the matrix vector, not the whole model scaling. The previous plot was for the whole model. So this is, as I move the sticks to the right, I'm quadrupling the resource. So the strong scaling is between the same pattern on the sticks. The weak scaling is you stick to the same colour and you can change the hashing, so at different local volumes. So for the whole model, we're seeing reasonable scaling up to, this is only running on 384 nodes because I'm profiling with Cray, and it's a bit difficult to profile out further than that. And if I look at the individual matrix vector, then I can see that the OpenMP version is going much faster, which is what I've just explained. So that's nice. Then the other thing we need to do to a solver is obviously the global sum. So this is the code. This is code that our Cyclone code generator would generate. So we do loop sharing, OpenMP work share across all the degrees of freedom for the local sum. That's what we're seeing there. And then we do a global sum on a single number, the scalar, which is then a call to this Earth system modelling framework, which ultimately maps down to MPI or reduce. And how does that scale? Okay, so if we look at the sum of local data on a single cell, then we call MPI or reduce on a scalar via ESMF. So the global communication, which we need to do a solver, that anti-scales some function of the number of MPI processors. It's just latency. Okay, so that's what we're seeing here. So this is what I'm trying to plot on the number of nodes and how long does it take to do that global sum. Then we see a really interesting thing, which comes from the Cray computer Aries network adaptive routing. So what route you get and how many links you use depends on what else is going on in the machine. This maximises the use of the network links because you've just paid all this money for this really expensive network, and if you only use a certain number of the links, then you're not getting full value out of those links. So you have adaptive routing. It depends what else is going on. But what route you take depends on the network traffic, even if you're confined to a small machine. So that's bad for operations because they really want to know exactly how long it's going to take, and that's a huge variation, right? I mean, that's, if the global sum takes 20 or 30 seconds and the variation was almost 100% of that. So this is just from 8 measurements. I've tried to do more measurements to see it, but basically, you see, as I use more nodes, it just takes longer to add up some numbers. There's large variation, so I've tried to show the best, the worst, and the mean just from 8 measurements. But it's not obvious when I get out here that 8 measurements is enough to actually pick up the best possible best case. Whereas here, down here, I thought we have got the best case. So the squares are with OpenMP and the circles are MPI only, and it's not completely clear that it says that doing OpenMP is better because there's less MPI ranks, so you have to do less global sums, or the cost of global sums is over less MPI ranks. But that's what I'm suggesting. If you look at the local communication, the Halo exchange is nearest neighbour and it scales with data size, that's bandwidth. So more OpenMP threads means less MPI ranks. It's a bigger Halo, fewer messages but with more data. That's kind of what MPI likes, fewer bigger messages. And that's what we see here. So if I do on the right is with OpenMP and on the left is MPI, and you can see that it's not obviously costing, well, this one does seem to be a bit higher. The cost of doing it that way doesn't appear to be significantly better. In principle, we can look at overlapping the comms of compute. We can also look at doing more or less redundant communication. We can look at redundant computation. We can try and do something called fuse kernels, where we share the horizontal looping for multiple kernels at the same time. So these are optimizations we can put in, that we have in the code generator. We can go and switch them on and see how and when they work, because they'll be data volume dependent and machine dependent. So does everything work yet? Well, no, not yet. Everything's still in development. And so this is the bit where everything's a bit speculative. And I've got lots of plots, and at some point I should stop. And take questions possibly. So we can try and do things with GPU as well. We're just going to target OpenACC to do this. So here's, for example, here's the actual code that is going to do this matrix vector as the kernel, and here is the parallelization layer code. I've hidden the MPI call because it's not relevant for this bit, but you can see with OpenACC you have to do move some data to a different space, and then you have to then do some looping. You also have to annotate a kernel and inject some source code in there. We can't do this yet. With Cyclone, it's something we're looking at how to develop. We can also look at doing things at individual kernels one at a time, just to pull them out the code to play around with some things. So this was done with some of our partners at IPC CDC Hartree Centre by Sergei Cisco. This is looking at the code optimizations for the local matrix assembly for the matrix vector, which is the thing I've been talking about a lot. This is on Knight's Landing. So this is just comparing different things. You can, if we change the loop order and put an OpenMP SIMD directive in, we can make the thing go faster. So this is looking at comparing on a GPU, NVIDIA Pascal, to KNL with a Cray compiler, KNL with the Intel compiler, and Broadwell with a Cray compiler, and looking at whether or not we should do the optimization. Then there's a number of reasons why this is unfair. I haven't included the cost of the data transfer on the GPU. I haven't got enough levels for the GPU, so it's both fair and it's unfair both ways around. I've got too many colours, not enough levels. But you can really see some interesting things already. GPU really likes that alternative loop order. The Cray compiler doesn't. It's already better. It doesn't care than Intel. The Intel wants the different loop order. Broadwell doesn't need the loop change, and KNL is not faster than Broadwell, which is, in terms of a design point for the Knight's Landing, that's a bit of a disappointment. You can try a higher order where I've got much more work to do. Nobody wants the different loop order. Wants the naive loop order. I can look at then running the whole model on Knight's Landing. This is comparing 6 nodes of Knight's Landing to 6 nodes of Broadwell. I can basically make it with optimizations, making Knight's Landing run as fast on Knight's Landing as I can on Broadwell. Okay, that's a minimum, isn't it, for Xeon Phi being a success? You probably want it to go faster, so that's a bit disappointing. We could probably do more, but it depends on how much work you need to do. But interesting, there's different features here. So if I use this different loop order to get a better optimization, which is the blue, then see, originally Broadwell is the black, and then this is this here. And then if I do it on Knight's Landing, naively, it's much slower. If I do this, change the loop order, it's much faster on Knight's Landing, so I get kind of the same kind of speed. Okay. If I oversubscribe concurrency and you use lots of threads on Knight's Landing, it goes faster. Right, that's what this sticks here. So we go, if I oversubscribe by 2, it's faster, and if I do even by 4, it's a little bit faster. So that's great. But if I put that optimization in, it doesn't go faster anymore. So somehow I can't get the same performance levers twice. I can pull one or pull the other one, but if I pull them both together, it doesn't go faster. So it's kind of it's a bit complicated. And then if you look at the volume dependence on Knight's Landing, if I have more cells, it just takes longer, right? Okay, that's what you'd expect. But if I increase the number of levels, which is the blue, and then count how much extra work that is, that puts doubling this number of levels is this much work, and it doesn't take twice as long. Okay, because I'm now going to start filling the vectors in the SIMD unit with more work. Okay, so that's good because we want more levels than 30. If I do it on a GPU, then it's even better. So the filled sticks are with just 30 levels. If I just make up extra levels with 4 times as many levels, that's 4 times as many work, then I get to the clear sticks. Okay, so it's taken longer, but nowhere near 4 times. Okay, so 4 times the black stick. Gone the wrong way. Sorry, operator failure. Right. So this is the naive runtime. If I increase the number of levels by 4, it only takes not very much longer. This is 4 times longer at that point there. So that's great. So I'm filling the vector. It's really working. But if I've done the optimization that makes it go faster, that's red, that's good, it makes it go faster. But now if I do 4 times the number of levels, yes, it's faster than 4 times the work, but not much. So again, I've only kind of got one lever and I've got 2 things to do, and if I pull them both at the same time, it doesn't really work anymore. It's a bit better, but nowhere near as good. So you can kind of have only one lot of performance gain by changing the loop order to get the extra performance. That's great, but if I want to fill up the vector with loads of levels, I've already used that performance, I can't get it again. So that's kind of tricky. So, what to optimize, and that's just a simple loop transformation in the simplest kernel. If I change the loop order, it depends on what compiler I'm using, what the architecture is, what the order of the method is, whether it's lowest order or higher, and what the data volume is. So this is just like makes that very difficult to write code, because it's always different. So can we maintain single science source code in this framework? Well, and then try and somehow decide how to transform loop order automatically. We'd have to inject source code into kernel code. Well, yes, we're looking at how we might do that. We would use special directives to do this. So the Meteo Swiss group, who are running on GPUs operationally, are developing their own compiler called Claw, which will do this for them. We look at polyhedral loop transformations. So there's all kind of computer science type research that we need to do in order to make to exploit the thing we've got with the domain-specific compiler to actually make this work. So, my sort of rather than conclusions have come to a summary. So weather and climate applications are very complicated. Models are very complicated systems. Exascale computing is forcing us to change what we're doing. We're having new algorithmic and numerical approaches, which I think are very interesting. We've got new software approaches to doing this. We've also got a really challenging timeline. So, the next HPC for the Met Office is around 2020 and a bit, something depending. And we want to have this new model to be operational halfway through that cycle, so about 2023. So we've got quite a lot of work to do. So in summary, what I think this is a very interesting project, which is why I joined the Met Office, and we've got a lot of challenges, and we're making some good progresses, but we've still got a long way to go. So, thank you.
Any questions?
I have a question. Unfortunately, it's about the weather and not about the computing.
Okay.
But, you mentioned something about the spatial resolution that you have in the models being either in the global model, I think 10 kilometers,
yes,
deterministic. What kind of temporal resolution do you have? So how quickly, or in what kind of time frames?
So the 10 kilometer model has about 5 minute time step.
Okay.
So we have a semi-implicit method. With an explicit method, then it's much cheaper to compute the solver because it'll be explicit. Your time step will be much shorter. It'll be down to less than a minute and seconds because of the CFL condition.
And when you do Monte Carlo simulation, when you do the ensemble averaging, so what would you get there if you're not looking just at the deterministic results? So do you know?
Yeah, so you can ask different things. You can ask for an ensemble, naively you can just ask an ensemble average and the variation. You can also do things like, well, if you're looking at storm tracks, for example, you can see, okay, 10 out of 18 show the storm track doing this, and 2 of them have a really different, interesting pattern, which is like a deepening, and the storm's being much worse, and it's going to go somewhere else. So, there's different. You can either pick out patterns and look at individual ones, or look at for extensive averaging across the ensemble.
And the kinds of products that you would normally be supplying to people in ocean modeling in terms of the resolution of wind forecasts. So how, if we're, you say you can get it to 5 minutes in the deterministic forecast, what would that, with the current capabilities that you have, in what temporal resolution can you update a wind forecast?
Yeah, it kind of depends. So the higher resolution model, the time step would be shorter. So 1.5 minutes for
1.5.
Yeah, so that's kind of challenging because you've got to do one time step. You want to go forward for 56 hours with 1.5 minutes. That's a lot of time steps to compute. It does give you very good temporal resolution, right? But it's a lot of computation. So.
Out of curiosity, the 18 realizations you do, is that just because that's the maximum that can be computed in the Monte Carlo simulations, or is it?
Well, okay, so not really. It's more kind of, well, that's a not too expensive number that gives us some confidence in computing effectively computing the error. I mean,
It doesn't sound very many.
no, it's not.
Yeah.
We could do more. If you're doing a climate run, you'd end up with a lot more, because then that space dramatically expands, because you have different evolution scenarios. Like if people stop chucking CO2 in the atmosphere, or people don't, and there's got ranges in between, so you have all that kind of fold in as well. But for a weather model, the size of ensembles is relatively small.
Is it big enough for tracking hurricane?
Yeah. So yeah, but if you do more, it costs more. You've got to do another model run. So it's in terms of the use of parallel computing, it's embarrassingly parallel. You literally run another model at the same time. So that's great for parallelism, but again, it's cost. So it's so they have a sort of cost-benefit analysis of what extra will they get. And again, with Monte Carlo, it's 1 over root n. Right, so if you do 10 times as many, you reduce the error by a third or whatever. So,
my understanding from your talk is that basically you're facing an optimization problem, a severe optimization problem in many respects. So you've got the equations, you've got the numerical maths dealing with them, and then you've got to put those on using optimized software and optimized hardware. But my question is, the equations are basically written in stone. Is that true? So there are no terms that basically, right? You could add there sub-leading terms which you haven't yet, and they obviously, if you have sub-leading terms, if you have neglected sub-leading terms in the equation, it wouldn't make sense to go to maybe that high an accuracy in your numerics. So what's the relation there?
yeah, so we pretty much have, the early weather models would have had neglected quite a few terms and made various approximations about hydrostatic balance and all kinds of things like this, which modern models don't. They're just pretty much solving the equations without really neglecting them. Clearly, there's obviously still 1 or 2 things.
There's an awful lot of filtering going on there,
Not in the current model. No, they used to do quite well. There's some filters.
Turbulence, winds, buildings.
So we ignore. Well, okay. So it depends what you mean by filtering. So in terms of the dynamics for the global model, there's just cut off at 10 kilometers, right? So any process smaller than that we don't see in the dynamics.
But once we filled it in as some sort of viscosity.
So we have physical parameterizations that come in, which then drive. So how accurate those physical parameterizations are? First, we have some kind of scheme or model for doing it, and then you've got to couple it and calibrate it with the model. And the point is then as ever increasing complexity, as more and more processes we include in models. So in that sense, yeah, there's a lot of. In that sense, so the dynamics, the dynamics are pretty much we're solving the dynamics, other than the fact that it's discretized, right? But in terms of processes that we don't resolve because, it's a turbulent system, you go, unless you're doing an atomistic simulation in the atmosphere, you will miss some fluid, some process going on. So in terms of things we don't resolve, yeah, there's any number of those we could add in, and people, that's what I'm saying about one of the slides I showed that we have about 20% code churn in the unified model. That's people putting in new processes. Right?
So maybe I missed it, but you gave us quite a lot about the scaling of the new model.
Yeah.
A direct comparison against the performance of the old model.
Yeah. So there's several. Yeah. So I haven't, and because we're not ready.
Well, maybe it's,
but the point is, okay. So let's find. Yes. So this is a good point, because people then at the Met Office are asking, is like, well, okay, is it any good? It's like, well, not yet, because where is it? Yeah, here we go. Okay, so in particular, the current unified model, the dynamics in the solver the system is called Endgame. And that's pretty well optimized, and it's a very good algorithm, and we're copying a lot of that algorithm here because they want to maintain the accuracy of Endgame but have it scale better. I mean, I've shown the plot where Endgame stops scaling, and we don't have all the bits yet. So in particular, we don't have we don't have the preconditioning we want, which will make a massive difference. And at the moment, also with the implementation we have, which is waiting on a couple of things, the timestamp is too small. It's only a few seconds rather than a few minutes for the problem size we want to do. So algorithmically, it's way off what we know, where we want to be in terms of performance. So if I compare those two things, it'll be really slow. I mean, once we get that going, then it's a legitimate comparison to see, and then it'll be more about, can I get the computational performance by doing optimizations automatically? Once we have something that's algorithmically much more equivalent and tunable. So we're not there yet. And the interesting one is things like local area models. Right, the local area model I showed you when I showed the scaling, that keeps scaling because it doesn't have a pole problem. Whereas if I compare that to a GOKHO local area model, I'm comparing a finite difference to a finite element model. And a finite element is much more expensive because you just do more things. You should get a higher accuracy at the same resolution, so then it's accuracy versus cost. So there's some definitely interesting comparisons to do, and the one where we should be able to win is by scaling to architecture in terms of architectures and the amount of parallelism that the UM can't on a global model. But we're not there yet.
Okay, so I'll end the formal questions now. If people have formal questions, they can talk to Chris. Okay, let's thank Chris again. Thank you.